Now let's move to the second technique of ensemble learning, which is called boosting. Boosting is an ensemble learning technique that aims to combine multiple weak learners into a strong learner. Unlike bugging, where base models are trained independently, boosting involves sequential learning, where each weak learner is trained to prioritize the data points misclassified by its preceding weak learners. The basic idea behind boosting is to focus on difficult instances, ensuring that they receive more attention during the learning process. This is what we will explain in the next slides, but what you need to keep in mind is that this approach results in a stronger learner that can effectively handle complex datasets and achieve high predictive accuracy. So let's explain how boosting technique works. In the boosting procedure, instances or training examples with higher errors are given higher weights compared to those with lower errors. The process typically involves the following steps. The first weak learner is trained on the original dataset with each instance carrying equal weight. After training, the errors are evaluated and the misclassified instances are identified. Then, those instances that are misclassified by the first weak learner are assigned higher weights to prioritize them in subsequent iterations. Instances that are correctly classified are assigned lower weights or may even be downsampled. The second weak learner is trained on the reweighted dataset, where the misclassified instances from the first weak learner receive higher emphasis. So the focus here of the second learner is to focus on learning the misclassified instances. Similarly, after training, errors are evaluated and weights are adjusted accordingly for the next iteration. Anyway, this will be in each weak learner, one by one in a serial fashion. Then the final model, after a predetermined number of iterations or until certain performance threshold is reached, the weak learners are combined into a final strong learner. So the final model effectively combines the strengths of multiple weak learners, with each contributing to areas where others may have struggled, resulting in a more accurate and robust ensemble model. So here we have a complementary role between weak learners. Each one is completing or taking over of what the previous weak learner failed to do, and so on and so forth, until we achieve like the final model. The boosting procedure involves the following steps. The first step is subsample generation. So for each iteration k from 1 to m, for example, let's consider that m equal 100, a random subsample x1, y1 until xn, yn is generated by randomly drawing m times without replacement from the original data. This differs from resampling with replacements, as seen in bugging. So the subsampled estimator is computed using the subsample data, and then in the next iteration, the next step, we have averaging subsampled estimator. So the subsampled estimator are averaged to approximate the final model. This is achieved by unweighted averaging or weighted averaging, where the weight represents like the weight of the kth estimator. In essence, boosting iteratively generates random subsamples from the original data, compute subsampled estimators using these subsamples, and then combines these estimators through averaging to approximate the final model F. The weighted averaging approach allows for the incorporation of different weights of each estimator, potentially enhancing the performance of the final model by emphasizing the contributions of more effective estimators. What is the difference then between Bayesian and Bayesian? So the comparison between Bayesian and Bayesian lies in their approach to model building. So Bayesian is a parallel computation model. In Bayesian, individual models are built separately and in parallel. Each model is trained independently on bootstrap samples of the data, and there is no interaction or dependency between the models. Then the final prediction is typically obtained by averaging the predictions of all models in the ensemble. However, Bayesian is sequential. In Bayesian, each new model is built sequentially and influenced by the performance of those built previously. The training process involves iteratively improving the model by focusing on instances that were misclassified by previous models. So each new model is trained to correct the errors made by the previous models with a focus on difficult instances that may have been misclassified. The final prediction is typically obtained by combining the predictions of all models in the ensemble, weighted by their performance during training. In summary, Bayesian involves building individual models independently and in parallel, while Bayesian involves building models sequentially, with each new model influenced by the performance of those built before it. So, what are the advantages of Bayesian? Actually, it has many advantages. One of them is its capability to learn any function. Given an appropriate weak learner, Bayesian is capable of learning complex functions and capturing intricate patterns in the data. The second advantage is feature weighting. Actually, Bayesian naturally assigns higher weights to more informative features, allowing it to focus on the most relevant aspects of the data during the learning process. The last advantage is the is that it has very little parameter tuning. Bayesian often requires minimal hyperparameter tuning compared to other algorithms, making it relatively easy to implement and can be used actually effectively and easily in various applications. Regarding the drawbacks of Bayesian, the first one, it can overfit data, and this is one of the worst drawbacks actually. So Bayesian can be prone to overfitting, especially when the dataset is small or noisy, and this will lead to reduced generalization performance on unseen data. So this, which means that Bayesian should be used with precaution when the dataset is small or noisy. The second drawback is its sensitivity to noise and outliers. Bayesian might struggle with noisy or outlier-rich datasets, as it tends to focus more on difficult instances during training, and this will potentially amplify the effect of the noise. Now let's move to the third technique of ensemble learning, which is called stacking. Stacking, also known as stacked generalization, is an ensemble learning technique that combines the predictions of multiple Bayes models to create more powerful models. Unlike other ensemble methods that directly combine predictions, stacking leverages the idea that Bayes models can learn different aspects of the data and provide valuable insights rather than final predictions. So these predictions or insights from the Bayes models are then used as features or input data for meta learner, also known as blender or a meta model. The meta learner learns to combine these predictions to make the final prediction. By leveraging the diverse perspectives of the Bayes models, stacking can often achieve better predictive performance than any individual Bayes model alone. This technique is particularly effective when base models have complementary strengths and weaknesses, allowing the meta-learner to learn from their collective knowledge and improve overall prediction accuracy. In stacking, the base models are first trained individually on the original data, and their predictions are then combined and used as input features for a meta model, instead of making final predictions directly, as we have said. So the base models generate predictions or insights about the data or about an aspect of the data which are fed into the meta model. The meta model then learns from these aggregated predictions to make the final predictions, which means that the meta model has as input or features the predictions made by base models. This approach allows the meta model to leverage the diverse perspectives of the base model and learns how to best combine their predictions or generated features in order to improve overall predictive accuracy. Let us consider an example where stacking can be applied. In this problem that we consider, we are tasked with predicting the likelihood of road accidents occurring at various locations in the city using a dataset containing features such as location coordinates, route types, weather conditions, time of the day, and day of the week. This task is crucial for enhancing road safety and implementing preventive measures to reduce the incidence of accidents. By leveraging machine learning techniques, we aim to develop a predictive model that can accurately estimate the probability of accidents based on the provided features. This model will enable stakeholders, such as transportation authorities and law enforcement agencies, to identify high-risk areas and implement targeted interventions to mitigate the risk of accidents and enhance overall road safety in the city. In this scenario, different machine learning models can be utilized to learn various aspects of the relationship between features and road accidents. Here we will consider three base models. The first one is decision tree model. This model can effectively learn the relationship between road types, traffic density, and accidents. For example, it can identify that accidents are more likely to occur on highways or in urban areas with heavy traffic congestion. The second model is a random forest model, which can handle complex relationships between features such as weather conditions, time of the day, and day of the week, and their impacts on accidents. It can discern patterns like increased accident rates during certain weather conditions or time of the day. And the last base model is CNN. Convolutional neural networks are suited for learning spatial patterns, making them ideal for analyzing the spatial distribution of road accidents. They can identify infrastructure states, hotspots, and cold spots in the city by analyzing spatial data like location coordinates or route types. Anyway, so by utilizing these diverse models, we can effectively capture different aspects of the relationship between features and the road accidents, thereby enhancing our understanding and predictive capabilities of road safety. Integrating the insights from these models can provide a comprehensive understanding of accident risk factors and aid in developing targeted interventions to prevent the accident and improve overall road safety. In the final step of the stacking ensemble technique, we can train a meta model such as multi-layer perceptron or a support vector machine on the new dataset generated from the outputs of the base models. This meta model learns to combine and leverage the extracted knowledge from the base models to make a final prediction. By training on aggregated predictions from the base models, the meta model can effectively learn the optimal way to weigh and combine these predictions to improve overall predictive accuracy. This approach enhances the ensemble's predictive power as it learns from ready and digested features from base models. Stacking actually is the most used technique in ensemble learning. It is a versatile ensemble technique utilized across various machine learning domains, including deep learning, although it's not exclusive to it. It effectively combines predictions from diverse base models using a meta model and effectively improve the predictive accuracy. Compared to boosting and bugging, stacking's architecture can offer enhanced interpretability as it integrates insights from different models to provide a more comprehensive understanding of the data. So it's very easy to interpret the results and how it can be, and also the predictions and how can be made.